Hey everybody, this is Mr. Bortnick for AP Calculus AB. Today we're working on our trigonometry overview. It is lesson 1, focusing on constructing and using the unit circle. Enjoy! All right, for today's lesson on constructing and using the unit circle, we've got a couple of items that we're going to be focusing on. Our agenda for today is first, what is the unit circle and what is it used for? Second, what are degrees and radians? And how do we convert from degrees to radians and back? Third, what are coterminal angles and what does that mean? Fourth, reviewing from geometry, special right triangles, 30, 60, 90, and 45, 45, 90 triangles. Fifth, actual construction of the unit circle with degrees, coordinates, and radians. And then finally, for number 6, finding sine, cosine, and tangent using the unit circle. All right, so the first question for us for today is, what is the unit circle? It is pretty much in the name of itself. If we think about like what the word unit means, unit is another way of saying the word one. And so simply all a unit circle is a circle, which I'll sort of freehand draw here. We'll say that that's a circle, close enough, such that the radius of the circle is 1. And so the center of the circle is at 0, 0. That is where our center is. And that's going to be true for any unit circle. And the radius of that circle is 1, which means that if we were to go along the axes, that would mean that this point here would be at 1, 0. Up here would be at 0, 1. Going in that negative direction, that would be negative 1, 0. And then down here would be 0, negative 1. So a unit circle is simply a circle centered at the origin with a radius of 1. And so that is a key piece for what we're going to be doing with our setup for today. Now, the unit circle is very useful. Specifically, we can use it in order to identify lots of trig values. But specifically, if you know how to draw a unit circle or you know how to read a unit circle, you can find sine of x, cosine of x, tangent of x for all sorts of values. And we could extend those, in fact, to our reciprocal trig functions like cosecant of x, secant of x, and cotangent of x. So there are 6 total trig functions. We could find all of those using our unit circle in a couple of different ways. Now, when was this actually useful? This came about over a long period of time in mathematics when obviously there were no calculators. And so it's a really nice thing that the unit circle actually helps us find exact values. So it helps find exact values for given trig functions, or for trig functions at given angles. While your calculator can do an estimate and it gives you a decimal answer sometimes for those estimates, we're going to be able to find today some real exact answers, and we'll know why they're exact answers using how we constructed it today, which is really nice. So that's what the unit circle is. Let's talk about degrees and radians. So what are degrees and radians, and how do you convert back and forth? We know just from general real life, or if we think about physics, that there are different ways of measuring things, right? So if we're talking about measurement, a very common thing that we measure maybe is distance. And we know that if we're measuring distance, that there's a bunch of different ways we could do that. We could do feet, we could do miles, we could do kilometers, I could do inches. There's all sorts of things that you could use in order to measure distance. But each of these things are different ways of measuring distance. Similarly, we know that there's lots of different ways of measuring weight, right? For example, we might use pounds to measure weight, or you might use kilograms if you're in a science class, or you might use ounces if you're, say, baking something. And so we know that each of these 3 things, they're all just different ways to measure weight, as are inches, feet, miles, and kilometers for measuring distance. Degrees and radians are also measurement types. They're specifically measurements for angles. And in the same way that we can measure distance using different measurement types, like inches, feet, miles, and kilometers, there are two main ways that we measure angles. One of them is degrees, and the other is radians. Those are our two main ways that we do that. Now, also, like other measurement systems, you can convert from inches to feet. You could convert from miles into kilometers and back and forth, depending upon what you need. You can convert from ounces to pounds. As with other measurement systems, we can do that same thing with degrees and radians. And the way that we do that is we need to keep in mind how a measurement works. So I'm going to draw just a little very tiny unit circle here. So here's our unit circle. Now, in general, if I'm measuring an angle, we normally say that an angle on a unit circle is measured from the positive x-axis. So this line is where an angle starts, on the positive x-axis. And that's just sort of for consistency purposes. You could measure angles from a bunch of different ways, but we measure it from on the positive x-axis. And so that's a useful thing to know. Now, from there, we can open upwards. So depending upon how we go around this circle, we could have angles going upwards from that line or angles going downwards from that line. Normally, if we're measuring upwards, like for example, if I were to draw this angle right here, if I were to call this my angle, we would call this a positive angle. So maybe this would be like positive 45 degrees, depending upon if it looks pretty close to a 45-degree angle, but maybe not exact. When we go upward from that line, from this horizontal line right here, we have positive angles going around in this direction. We, however, can also have angles going in the negative direction. So if I erase these, we could also have an angle going in the negative direction. So for example, if I were to go from this line going downwards, and I were to measure this angle right here, this might be like a negative 45-degree angle. And that negative is just simply emphasizing that instead of going from the positive direction upwards, I'm actually going downwards from that starting line that we have right here. So angles could be positive or they could be negative. That's useful. Now, in addition, thinking back to some facts that we know from geometry, we know that a circle, if you go all the way around it, a whole circle is 360 degrees, right? If you measure an angle, if we have this line that's right here and we measure this angle that's going all the way around, that would be 360 degrees. In terms of radians, we call that distance around the circle 2 pi radians. It is 2 pi radians. So the same thing, if we were going to measure that distance going around the circle, that angle going all the way around, back to complete the whole circle, we would call that 2 pi radians. Similarly, if we were to think about a half a circle, we could cut both of those values in half, right? So if we have our half circle, that's sort of like this, and we only go halfway around, we would say that that's 180 degrees, right? That's half of the 360 degrees. Or if we're talking about radians, it would be half of that 2 pi, or pi radians. Now, the question then is, so we can see that for various angles, that the relationship is essentially proportional, right? 360 degrees is 2 pi. 180 degrees is pi radians. So we have some very clear benchmarks as to what degrees match up with what radians. Because of that, we can essentially create a formula and a unit conversion thing. For example, I'm going to just sort of erase this for right now just so we've got a little bit more room. But for example, if I have something in degrees, to convert it, what I would multiply by is I would need to multiply by the ratio of radians over degrees. And so I'm going to use my half circle here to set those up, but that ratio here would be multiplying by pi over 180. So if I take the degrees and I multiply by pi over 180, that is going to give me the same exact angle in radians. So this is a useful equation to know. And I can do the opposite. I can convert from radians into degrees by multiplying by the reciprocal of that fraction. And if we think about where those things are, if we were to multiply by the reciprocal, this equation would still be true. So both of these are useful equations to have, simply that degrees times pi over 180 is equal to radians, and if you're converting from radians to degrees, radians times 180 over pi is equal to degrees. So with that said, let's get into how we're going to do this. I am going to be using a calculator for some simplification along the way. I encourage you to have your calculator out if you want to follow along. So in number 1, in this problem, I have 5 pi over 3. They're asking us here to convert each degree measure into radians and each radian measure into degrees. I know that this is currently a radian measure because it's in terms of pi, as opposed to like having a degree symbol like we see like in number 6. And so in this case, I'm going to use this formula, radians times 180 over pi is equal to degrees. If I wanted to simplify that and figure out what this would be for degrees, we could say that we could just multiply this by 180 over pi. And what we can see here is that actually our pi's are going to cancel out, which is sort of nice. And so this is going to be equal to whatever 5 times 180 over 3 is. So 5 times 180 over 3, and that is going to be equal to 300 degrees. So 5 pi over 3 is the same thing as 300 degrees. Sometimes it's going to be useful for us if we're not sure what a particular angle is. It's useful to frequently in geometry and in earlier grade levels, we often think about degrees. And so even for me, I'm generally more comfortable thinking about something in degrees. And so if I'm having trouble visualizing an angle, sometimes I will convert it just so that I know exactly where it is and I can be confident in it. But as you work more and more with radians, especially in AP Calculus, you're going to get more comfortable with it, just like everything else. We can do the same idea for number 3. So in this case, if I wanted to convert this radians to degrees, I'd multiply by that 180 over pi. Our pi's would cancel each other out. So that's 7 times 180 over 4. 7 times 180 over 4 in our calculator would be equal to 315 degrees. So 7 pi over 4 and 315 degrees are equivalent. They're just different measures of angles. We can do this also in problems like number 7, where they give us a degree, like we have right here, and we need to convert to radians. So in that case, we would use this equation where we multiply by pi over 180. Again, these unit conversions are coming from this half circle idea where we know that 180 degrees is the same thing as pi radians. So we're using that in these unit conversions to help us to get from one form to another. But what would we multiply by here? We're multiplying by that pi over 180. And so in this case, I have 240 pi over 180. And I would simply need to simplify that fraction. So 240 over 180, if we were going to simplify that, that looks like that would be 4/3. And that pi is still there. So this is the same thing as 4 pi over 3 if we were going to simplify that fraction, right? Both of these things are divisible by 60, and so we get 4 pi over 3. We can do the same idea for any of these practice problems, and I encourage you to do that. This is also true for negative angles, right? We have that as well, but the format would not change. I would just simply have a negative radian here. I'd have a negative degree here when I did that. That is how degrees and radians work and how we convert back and forth. Now, why are we talking about both of these? Well, our goal today is to discuss the unit circle. And the unit circle itself, if we do that, shows us both the trig values, sine, cosine, tangent, cosecant, secant, cotangent, in degrees and radians. So we need to know what both of those things are leading into this. Great, feel good about that. A reminder, right? This is a video specifically for my AP Calculus students. Almost always, trigonometric problems use radians in this class. And so as we go along throughout this year, you are going to be seeing, sine, cosine, tangent with respect to angles measured in radians. It is incredibly important to make sure that your calculator is in radian mode when using any trig functions in this class. Sometimes for those of you who are like in AP Physics, you might need degree mode from time to time. Please make sure anytime this year, if you're doing sine, cosine, tangent, any of those trig functions, your calculator is in radian mode if you're doing AP Calculus, because that is what they expect on the exam. And we know that part of the exam at the end of the year is going to be calculator allowed, so we'll want to make sure that we're in the right mode and getting the correct answers for that. While I'm talking about answers using calculators, also a reminder that we always round our answers. So we always round our answers to 3 digits after the decimal place. That is true anytime you are rounding in AP Calculus. So I would two real big things with your calculator. Make sure it's in radian mode, and if you ever round in AP Calculus on the free response section, that you are rounding to 3 digits after the decimal place. And so an example of that is if I had like a number like 1, 2, 3, 4, 5, 6, 7. That's our number. If we were going to round to 3 digits after the decimal place, that would look like this. So 4.123. That would be my answer for that rounded work. You could either truncate it, aka cut all of those digits off after the 3rd digit, or you can round. So if this were like a 9 here, then maybe this would become a 4 if that were the case. So in this case, if that were a 9, then 4.123 would be acceptable, or 4.124 would be acceptable. But we always round answers to 3 digits after the decimal place in AP Calculus. All right, let's keep going. So next, let's talk about coterminal angles. Coterminal angles are angles in standard position, aka angles with the initial side on the positive x-axis. So this is our standard position, is that positive x-axis, that have a common terminal or ending side. So for example, we can see that this angle right here, this angle right here is 30 degrees, right? That's our 30-degree angle. And this also says the angles 30, 390, and even negative 330 are all what they call coterminal. What does that mean? Well, if we erase this, we notice that we've got this 30-degree angle, which I've got highlighted here in green, right? This is our 30-degree angle. If we were to start over again, so I'm starting on this positive x-axis. If I went all the way around, so all the way around the circle, we know that that would be 360 degrees, right? Because a whole circle is 360. But if we kept going, ooh, it made a circle. If we kept going around that, that's useful. If we went another 30 degrees, we would end up right here, which you'll notice this line is what they're calling the terminal side. So what does that mean? That means that 30 degrees and 390 end up at the same line. They end up at the same line. And since this is a circle, you could actually go around the circle as many times as you need to in order to get to a particular angle. So this comes up frequently if you think about extreme sports. If I think about skateboarding tricks or snowboarding or things like that, we know that if we were to like jump in the air and spin around, that we would call that a 360. And we also know that if we were to jump in the air and spin around twice, they refer to that as like a 720, right? That's 2 360s. And if you're getting really good and you somehow jumped up in the air and spun around 3 times, we would call that a 1080, right? Because that's 360 times 3. And so all of these angles are equivalent, right? If I imagined jumping in the air and spinning around, and I went exactly around and I landed in the exact same spot facing the same direction, we would be 360 degrees turned. If I did that twice, I would end up still facing the exact same way where I started. And if I turned 3 times all the way around, I would still end up facing the exact same way as well. So it's possible, you could have a bunch of different angles that are actually technically the same angle, right? They end up at the same terminal side by going around the circle a certain number of times. Now, as we had said before, you could actually go around a circle in the positive direction or the negative direction. So if we were to start off at our initial side right here in red, and we went in the opposite direction, This is our negative direction. And we ended up right here, 330 degrees, right? This is negative 330 degrees. It also ends on this exact same side. So it's interesting that 30 degrees, 390 degrees, and negative 330 are all coterminal. They all end up at that exact same angle. They're all going to give the same values. In fact, if I were to, for example, find sine of 30, that's going to equal whatever sine of 390 is, which is also going to equal sine of negative 330. You can test that in your calculator if you don't believe me, but that's true for any coterminal angles that end up at that same exact point. Which means it's actually useful if I get a problem like, ooh, find the sine of 390, for me to convert it down to sine of 30 degrees, because I know what 30 degrees looks like, but I don't necessarily know what 390 looks like. And so in general, if they were to say, to write a coterminal angle, or to write angles that were the same, if they gave you, say, 1,000 degree angle and we wanted to know what that was equivalent to, one thing that we could do is we could just subtract 360 a couple of times. And so specifically, if we take that 1,000 and you subtract two 360s, so 1,000 minus two 360s, so that's taking two circles away, that's the same thing as a 280 degree angle. So if I think about where 280 is on a unit circle, if this is my unit circle here, 280 is about right here. So this would be 280 if I started right here and I ended right here. This angle around here would be about 280 degrees to go from there to there. And that's the positive direction. My argument that I'm making is I'm saying that these are coterminal. They're going to end up in the exact same spot if I draw another unit circle, and I draw now in green for this 1,000 degree angle, that if I started on this line that we've got right here, I would actually go around the circle once, like we see here. I would go around the circle twice, so once, twice, and then I would keep going until I got to this exact same line that I had right here. This would be all my 1,000 degrees, just where I'm ending, notice, in the exact same spot as this one right here. So they're ending up in the same spot. They're both have terminal sides that are in the same spot, which means that their sine values, cosine values, tangent values would all be equivalent to each other. That's nice. We can do the same technique of either adding or subtracting whole circles with radians or degrees. And so if something were in radians, for example, if I wanted to think about, let's say I've got a negative pi over 4 radians, and I wanted to figure out what that is on my standard unit circle, one thing that I could do is I could actually add a whole circle to it. So we know that in radians, a whole circle is 2 pi, right? And similar, we were subtracting a whole circle here because we had a number that was bigger than 360. Here we have a negative number, so I'm adding a circle to it to hopefully make it positive. And if I were to do this and I had no calculator, well, in this case, I would want them to have a common denominator. So I notice that 2 pi technically has a denominator of 1, so I'm going to multiply by 4 over 4. So I've got negative pi over 4 plus 8 pi over 4. And then now, since these have the same denominator, I'm going to add going straight across. Negative pi plus 8 pi is the same thing as 7 pi, and that's being divided by 4. So what I'm saying is that negative pi over 4 and 7 pi over 4 are coterminal angles. They end up at the exact same spot, and these would have equivalent values for both sine, cosine, tangent, cosecant, secant, cotangent. That's useful. Again, the only reason I'm really talking about this is that sometimes you get angles that are negative, right? This is specifically to deal with times when you have negative angles. And sometimes you have angles that are greater than 360 degrees or 2 pi. And so that's how you would handle situations like that if they were to come up in AP Calculus. All right, now we have laid the groundwork. We are ready to get into our actual construction of the unit circle. And in order to do that, we need to talk and go back to geometry. specifically talking about special right triangles, 30, 60, 90 triangles, and 45, 45, 90 triangles. These triangles are fundamental to being able to work with the unit circle. So, with that said, let's talk about what we know. So for a 30, 60, 90 triangle, the way that we sort of think about the relationships with that is I sort of think about the 30, 60, 90 triangle as half of an equilateral triangle, right? If we imagine that this is a 60 and that this is 30, that this whole big triangle out here would be an equilateral triangle. And so if I were to, for example, say that this side length here is x, that hypotenuse of this right triangle that we've got here, that would mean for this whole big triangle that we've got here that this over here would be x and this whole length over here would be x, right? This whole length from there to there would be x. But since this is only half of that equilateral triangle, that means that this is not the full distance from here to here, but it's half of that, which means this is going to be x over 2 if I'm going from here to here. Then we know that since this is a right triangle, that the Pythagorean Theorem applies. And so you might remember your a squared plus b squared is equal to c squared. If I'm trying to figure out, I'll call this my b here. What is that b? We can say that we've got x over 2 squared plus whatever b squared is equal to our hypotenuse squared, which is x squared. If we were to expand that out, we would get that this is x squared over 4 plus b squared is equal to x squared. I am going to subtract this x squared over 2 here to the other side. So that means that b squared is equal to x squared minus x squared over 4. And similarly, if I'm going to be able to combine these, they need to have the same denominator. So this is technically like x squared over 1 right now. What I'm going to do here is I'm going to multiply by 4 over 4. And so now we get that this is b squared is equal to 4x squared over 4 minus x squared over 4. Subtracting those numerators, 4x squared minus x squared is going to be 3x squared. So b squared equals 3x squared over 4. And then to get that b by itself, we take the square root. So b equals the square root of 3x squared over 4, which is going to be equal to the square root of 3 times whatever our x is over 2. So what does that tell us? It tells us that if we go back up here, that this is going to be whatever our x value is times root 3 over 2. Which is sort of nice. This is a relationship that's going to be true for any 30, 60, 90 triangle that we've got here. So root 3 over 2 times the x value is going to give us that. And similarly, this is going to be 1/2 times that x value. If we jump to that 45, 45, 90 triangle that we've got over here, and I want to try to relate the sides here for this, one thing that's nice about a 45, 45, 90 triangle is if you remember, if the base angles are the same in a triangle, that means that it's an isosceles triangle. So I know that these two sides have to be equal to each other. So I'm going to refer to both of these as our x, right? They're going to be the same, whatever that is, I'm going to call that x. And if I want to find the hypotenuse here, I'll call that c, because we're doing our Pythagorean theorem again. If we do that, a squared plus b squared is equal to c squared. In this case, we have x squared plus x squared is equal to c squared. And so I have 2 x squareds is equal to c squared. And I want to take the square root of both sides. So if we take the square root of both sides, we get that c is equal to the square root of x squared, which is x, times the square root of 2. So root 2x is equal to our c value. So the square root of 2 times x is going to always be that hypotenuse. So for example, if I'm given a problem and I know that I've got a 45, 45, 90 triangle here, and I know that this side is 2, Using these relationships here, I know first off that these two are going to be the same, so that would mean that this side would have to be 2 as well. And then we notice that the hypotenuse is square root of 2 times whatever that side length is, so that would be 2 root 2 if we did that. We can do similar ideas with these 30, 60, 90 triangles. You know, for example, if they gave you a triangle like this, and here's your 30, here's your 60, here's your 90. If we knew, for example, that this side right here was, let's say, actually this one down here is 2, then we know that whatever this is, right, this is half of whatever this is, which means that if this is 2, this has to be 4 up here. And then the relationship between the two of these is that this third side is whatever this side is times root 3 over 2. So that would mean that this is actually 4 root 3 over 2 for that third side. Now obviously we could always do the Pythagorean Theorem to find those missing sides, but it's nice to have these relationships and know ahead of time what these values are going to equal. We're going to use this in the unit circle next. How are we going to use it? Well, let's do this with some brand new clean triangles that we've got here. What we know about the unit circle, if we go way back to what we said at the beginning, we said that the thing that makes the unit circle is it is a circle that is the center is at the origin, right? It's at 0, 0, and it has a radius of 1. What we can do using this unit circle is I can sort of actually draw some arbitrary angles. So let's use orange to make this pop. I can essentially make triangles on this unit circle that are based on the coordinates. But one of the things to notice about this is that because this is a unit circle, we have a line that's going from the center of the circle to the edge of the circle. That means that for sure that this line, this hypotenuse, would have to be 1 because it's going from the center to the edge. And we know that the radius of that unit circle is 1. So since we're going to be using a lot with our unit circle here, I want to do these exact same relationships that we found for 30, 60, 90 triangles and 45, 45, 90 triangles with our two special triangles here, specifically with a hypotenuse of 1. Well, how would that look? Well, in this case, we know that if in our 30, 60, 90 triangle, that if this is 1, that this is half of that length. So half of 1 is going to give us a side length of 1/2 down here. And we also know from up here that the relationship between these two is that it's whatever this side is times the square root of 3 over 2. So since this is 1, that means that this side length here would be the square root of 3 over 2. Nice. If we look back at our 45, 45, 90, we see that whatever this length is over here, whatever these are, if you multiply by the square root of 2, you're going to have your hypotenuse. But here we have the hypotenuse already, which means I need to actually divide by the square root of 2 to get these two sides that are over here. So if I were to do 1 divided by the square root of 2, well, that's not a really good denominator, right? We don't leave square roots in our denominator. So I'm going to multiply by the square root of 2 over the square root of 2. And if we do that, we get that this is the square root of 2 over the square root of 4, which is 2 in that denominator. And so this is equivalent, our 1 over the square root of 2 is the equivalent to root 2 over 2. And so both of these side lengths are going to be root 2 over 2. So in special right triangles where the hypotenuse is 1, this is sort of a key piece because we're going to be using this here in a little bit, right? These are both special right triangles where the hypotenuse is 1. We already know what the side lengths are, which is great. We're going to use that next. All right. With the video file for this, I will be posting both this PDF that I'm going through and then also a blank unit circle and a completed unit circle. My goal now is I'm going to talk about how we construct the unit circle from scratch. How do we do that? So we're going to start with what we know. We know that the unit circle starts at the origin, right? The center is at the origin, and it has a radius of 1. As we talked about earlier, that helps us find some coordinates. For specifically, I know that this point right here is 1, 0, because it's 1 unit right. Here, if we went up, that's going to be 0, 1. If we went to the left, that's going to be -1, 0. And if we went down, that's going to be at 0, -1. Those are pretty straightforward just from using the definition of what the unit circle is. And again, I'm just trying to find the coordinates here of those first couple pieces. Now, in addition to that, we know that, we'll talk about degrees next. We know that all angles are measured from this line. So this line is technically 0 degrees. This, what I'm going to put as a red line, that is where all angles start, right? That's where we start measuring angles from. If we go up to here, we can see that this line right here is a 90-degree angle. So I would expect up here to be 90 degrees for this line that we've got right here going vertically. Right? So the angle from here to here would be 90 degrees. If we went halfway through the circle from here to here, that angle is going to be a 180-degree angle. If we went another 90 degrees from there to there, 180 plus 90 is 270. And then if we went back to where we started, if we went all the way around the circle, back to where we started, a whole circle is 360 degrees. So that's useful for degrees. Now, how do we find out all the rest of these lines that are on this unit circle? Well, we notice that from 0 degrees to 90 degrees, if we go halfway, which is this line right here, half of 90 degrees is going to be 45 degrees. So that's going to be a 45-degree angle. Again, that's the angle going from this red line to this line right here. And what we also might notice for these two that are right here is that these three lines, I'm going to actually draw here in green, if I go from this line here to this line here to this line here to this line here, all of these 4 lines here in green, those are split up into 3 parts. Right? This angle is the same as this angle, which is the same as this angle. And since that whole angle together is 90 degrees, that means that each of these is 30 degrees. So since this was 0 right here, that means that this angle right here is going to be 30 degrees. If I go another 30 degrees more, that means that this is 60 degrees. And if I go another 30 degrees more, we get back to 90 degrees. Now, I can actually follow that pattern going all the way around, going by 30 degrees, and I'm going to do that. So 90 plus another 30 would mean that this is 120. If we go another 30, that's going to be 150. Notice I skipped that line. If we go another 30, that's going to be 180. If we go another 30, that's going to be 210. If we go another 30, that's going to go to right here, which is going to be 240. Another 30 would get us to 270. Another 30 would get us to 300. Another 30, going from here to here, would be to 330. And then if we go an additional 30, we'd be back to 360. So we can go around the unit circle in degrees by 30 degrees, which is nice. But similarly, what we showed, so I'm going to erase what we've got here in the middle. Similarly, as we showed, if I take a different color, let's do this in blue now, that this angle here to this angle right here was 45 degrees. That is the same as from this line to this line is also 45 degrees. 0 to 45 is 45. 45 to 90 is another 45. So for these lines that are here that we haven't filled in yet, those are going up by 45-degree angles. So what do we have? Well, we have, again, that this one right here is 45. If we go another 45, that's 90. If we go another 45, that's 135. Going another 45, that's 180. Another 45, that's going to put us at 225. If we go another 45, that's 270. If we go another 45, that's going to be 315. And then if we go another 45, we're back to 360, and we've done that whole circle. So at this point, what I've done is I've been able to label all of the degrees for our unit circle. Right? We went from 0 all the way up to 360. Really noticing that these middle lines here in blue are going by increments of 45 degrees as we go along, and that these other two lines in each of these quadrants is going up by 30 degrees. Sometimes it's useful also, people notice that these quadrants are always set up where they go 30 degrees, then 15 more degrees, then 15 more degrees, then 30 degrees. Whatever way is helpful for you to be able to produce this, if you needed to replicate it. Sometimes, you know, if I were an AP Calculus student and I were in the middle of an AP exam and I needed to think of a sine or cosine or tan value, sometimes students actually draw out a little unit circle from scratch, from memory, in order to help find those values. So it is useful to know to be able to understand and to practice being able to add the degrees and the radians and those coordinates. Now, let's get into radians. I think that's going to be the easiest to do next. So radians we'll do here in red. We know that, again, they start off at this line, this positive x-axis. So it is 0 radians is where that's going to start. We also know that if we went all the way around the circle back to this starting line, that would be a whole circle, which in radians is 2 pi radians. So it's 2 pi radians if we do that. Which means that half of a circle is pi radians. And if we think about, well, if I'm going half of a circle is pi, that means if I go half of a circle, aka a quarter of a circle, that's going to be half of this value. So it's going to be pi over 2 radians. And 45 degrees is half of 90, which means that whatever this angle is should be half of our pi over 2. If we do pi over 2 divided by 2, well, that's pi over 4. Similarly, we also said, and actually I'll stick with that for right now, we also said with these blue angles here in degrees that these were going up by a consistent amount each time, 45, 45, 45, 45, 45, all the way around. It's going to be the same thing for our radians. So this is pi over 4 is the same thing as 45. I would go another pi over 4, another pi over 4, another pi over 4, another pi over 4, until I got back to that 360. So one way that I actually do this, if I am trying to do this quickly, or even thoroughly, it depends on if it's quick or thorough, but I'm going to think about the multiples of pi over 4. 4 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, all the way up to 8 pi over 4. And why would I stop at 8 pi over 4? Well, that's the same thing as 2 pi. So I'm just thinking about the values between this. So why am I doing this? Well, pi over 4 we already did. That's on our unit circle, right? We've got that. That's on here. 2 pi over 4 would be another pi over 4 units, right? Or 45 degrees. And so if I simplify that, this is the same thing as pi over 2, which we see is on our unit circle up here. Our next angle is going to be another pi over 4 units. That's 3 pi over 4. So this is 3 pi over 4 right there at that point. So that's on our unit circle now. If we go another 45 degrees or pi over 4 radians, we end up at 4 pi over 4, which simplifies to become pi. And we've got that on our unit circle, which is great. If we go another 45 degrees or pi over 4 radians, we're going to end up at 5 pi over 4. If we go another 45 degrees or pi over 4 radians, we're going to end up at 6 pi over 4, but that simplifies to become 3 pi over 2. And that's going to be this angle right here. If we go another 45 degrees or pi over 4 radians, we're going to end up at 315 degrees or 7 pi over 4 radians. And then if we go finally another pi over 4 or 45 degrees, we're going to end up at 8 pi over 4, which is the same thing as 2 pi, and we've got that right here if we go all the way around the circle. So we've got those radians on there for the multiples of 45 degrees or pi over 4. We can do this exact same concept that I just did with our 30-degree angles or pi over 6 angles. So how did I know it was pi over 6? Well, I'm going to erase this all here on the bottom right here because we're going to do a similar concept for this. We know that this angle right here is pi over 2, right? And if what we remember from before is we had said that this angle right here is the same as the angle right here is the same as this angle right here. This is the same, each of those three things. It's split into three parts. So what we did earlier to figure out what this angle was is we said, okay, well, let's take that 90 and divide it by 3. We get 30 to find out what that angle is, right, to go from here to here. I'm going to do that exact same idea, except I need to divide that pi over 2 in radians by 3. If I do that, that's going to be pi over 6. So that's where that comes from. This is pi over 6 right there for that value. Now, same as what we did before, we went around the circle here for these blue ones, for these dark blue, or these purple ones. We went by 30 degrees all the way around. 30, an extra 30, another 30, another 30, another 30, till we got all the way around. I'm going to do that exact same idea with radians. And in order to do that, I'm going to write out my multiples of pi over 6. So 1 pi over 6, 2 pi over 6, 3 pi over 6, all the way up to 12 pi over 6. So give me one moment to do that. Now a reminder, you know, this is meant as a review. I know that for some of us, this might be the first time that we're going through this material. This is one of those things that practice is super helpful. I'm good at explaining it because I've done this multiple times and can do the unit circle from memory. It normally takes a bit of practice in order to do that. So I encourage you, after you've watched this video, to try to grab a blank unit circle and to try to fill these values in yourself and see what you remember from the explanations. Everything that we're adding to this unit circle has a reason, and I'm hopefully explaining those reasons along the way so you can remember and be able to create this on your own. So what I've done here for our radians to wrap the radians up is we've got all of the radians from pi over 6 all the way up to 12 pi over 6. Right? We've got all of those. And we know, again, that it's adding a pi over 6 or 30 degrees every time we go to this next sort of like purple angle that we've got here. All these missing ones that we've got. So let's simplify some of these. We see, do I want that one? I'll do it in green for these, I think. So we see for this first one that we said that this angle right here was pi over 6. We've got that on our unit circle already. If we go another pi over 6 units or 30 degrees, we're at 2 pi over 6, which simplifies to be pi over 3. So pi over 3 is our next angle that we've got right here. If we go another 30 degrees or pi over 6, we're at 3 pi over 6, but that simplifies to be pi over 2, which we see on our unit circle already right here. So we're going to go another 30 degrees, which will take us to that. 4 pi over 6 simplifies to become 2 pi over 3, which is what our next radian is. If we go an additional angle, we're at now 5 pi over 6, which does not simplify, so we'll just put that, 5 pi over 6. If we go another 30 degrees or pi over 6 radians, we're going to be at 6 pi over 6, which is the same thing as pi, and we see that that's on here already, which is great. If we go that additional 30 degrees or pi over 6, we're at now 7 pi over 6, which does not simplify, so I'll leave that. If we go further, we'll be at 8 pi over 6, which simplifies to become 4 pi over 3, which is this angle right here. Another 30 degrees or pi over 6 is going to be 9 pi over 6, which simplifies to be 3 pi over 2. We see that already on our unit circle from earlier. 10 pi over 6 simplifies to be 5 pi over 3. That's going to be this angle right here. And then we've got both of those on here. 11 pi over 6 is next. And then finally 12 pi over 6 is the same thing as 2 pi, which we already have on our unit circle. Okay. We have all of the degrees, we have all of the radians on here. And that was a fair amount of work just trying to think about how do we split this up. Now, a big part of what we're doing today is not just, constructing this, but also reading it. So we need to know what do these values tell us? This is a nice conversion for us from earlier, right? We know we have that formula to convert from degrees to radians. But first off, looking at our unit circle, we can see degrees and radians that are equivalent for each of these lines, right? Degrees and radians are the same. These are what each of these would be if we use those formulas that we talked about earlier in today's lesson. Now, the only thing that we're missing are these coordinates on the outside. We have already found some of the coordinates, right, because we knew that this was a unit circle and it had a radius of 1. But some of these are really difficult to find, right? I know that this distance here is 1 because it's the radius of the circle, but I don't necessarily know, how far to the right and how far up am I going. In fact, they're not particularly nice numbers, and so we need to think about how we can approach that. So I'm going to get rid of our work that was down here. And what we're going to do to find those is I want to sort of draw what we've got for this first angle. So let's talk about how to find this angle right here. So I'm looking at this angle. What I'm going to do is I'm going to essentially draw a straight line going down towards the x-axis from that line. If we do that, we are going to end up with a right triangle that looks something like this. So here's our right triangle. Now we know from the work that we've done here that this is a 30-degree angle. This line, these give me 30 degrees, which means that I've got a 30, 60, 90 triangle. We also know that the hypotenuse of this line right here is going to be 1 because it's going from the center to the edge of that circle. That's going to be 1 unit. This looks really familiar. In fact, we actually already found the side lengths for this back when we did this 30, 60, 90 triangle. In fact, we saw that when the hypotenuse is 1 in a 30, 60, 90 triangle, that the side across from the angle 30 is 1/2, and the side across from the 60 is √3/2. So I'm not going to do that over again. I just know that this is going to be 1/2, and this is going to be √3/2. So, and again, we could use our 30, 60, 90 degree relationships in order to find that, but that was essentially what we did all on this previous page. So, that's nice. I know what those side lengths are. How does that help me find this coordinate? Well, we know that for this particular triangle, this triangle, is right here if we're looking at it, here in green. What we know is that this is at 0, 0, and I'm trying to find out what this coordinate is that's at this point. I'm going to say just like x, y. We notice that since this is a coordinate plane, to get from 0, 0 to this point up here, I have to go right, and then I have to go up. So I'm going to go right √3/2 units, and I'm going to go up 1/2 unit. That would mean that if I start at 0, 0, and I went right 3/2 and up 1/2, that's actually the coordinate for this. And so if we take a look at our coordinate up here, this is going to be at, let's get a more fun color. This is going to be at √3/2, 1/2. √3/2, 1/2 for that particular point. Now, I can use the same reasoning for my next angle, which if I do that appears to be a 45 degree angle. We've got 45, 45, 90. The hypotenuse is 1. We said earlier that the side lengths have to be √2/2 and √2/2. And conveniently for us, that would be our x and y values for this. √2/2 and √2/2. I can do this for really any angle on here. And so what we've got, up here, if we were to do the same thing, 60, 60, 90 triangle, this would be 1/2 in the x direction and √3/2. But what happens over here when, they're on this part of the line? Well, in this case, what we see here is if I were to draw this triangle, the triangle would be going down to our x-axis, it would be going up to here. And so what do we have if we do that? Well, if we draw that triangle that we have, we see that this is a 120 degree angle. So that means it's 120 degrees from here to the positive x-axis. So if I was thinking about from the 120 to 180 to get down to the x-axis, that means that this is a 60 degree angle again, which means that this is 30 and this is 90. And again, for this line, we have a line going from the center all the way to the edge. That is going to be a length of 1 because this is a unit circle. And then again, thinking about our relationships from earlier, about 30, 60, 90 triangles, that means that this is 1/2 and this is root 3 over 2. Well, in this case, our scenario, this triangle that we had right here, right, this was our triangle, the origin is this point that's right here. This is 0, 0, which means that to get to this point up here, which is the coordinate that I'm trying to find, right, my x, y, I had to go left 1/2, and I had to go up root 3 over 2. I had to go left 1/2 from the origin, and I had to go root 3 over 2. If I go left, I'm going in the negative x direction, and if I go up, I'm going in the positive y direction. That means that this point up here is going to be at negative 1/2, because we went in the negative, and then positive root 3 over 2, because we went in the positive y direction. So all this particular angle right here, if we're doing this, would be negative 1/2 root 3 over 2. We could do the same idea with this 45, 45, 90 triangle and say that this is negative root 2 over 2, comma positive root 2 over 2, and that this is then negative root 3 over 2, comma positive 1/2. This same idea of using these right triangles to find these angles is the way that I would fill in the rest of this. Keep in mind that these values down here, right, if we were to draw this, would have negative x values and negative y values, right? Because we're going to the left, we're going down. Going left, down, left, down. So I'd expect all of the values here in this third quadrant to be negative. And while we're talking about quadrants, the way that we name these quadrants, this is our first quadrant, this is our second quadrant, this is our third quadrant, this is our fourth quadrant. And the quadrants are numbered going around, starting from that 0 degree angle. We hit this first one first, then this one second, then this one third, then this one fourth as we go around. For these angles down here in quadrant 4, if I want to find these particular values that we've got here, we notice that we would go right and down to get them, which means that the x value is positive, but the y value is negative. I'm going to jump now to the actual unit circle. So again, this was posted in our files with this video. This is our completed unit circle. It's got our degrees, it's got our radians, it's got our coordinates, our x and our y values. I talked up here about how we would create one of these or where all of those numbers come from. But generally, this is a great tool to help us find sine and cosine and tangent. How does that work? Well, if we're going to find sine and cosine and tangent using the unit circle, if we've got a completed unit circle or if we sketch one on our page, we can think about a triangle that's being drawn. So specifically, we know that going from the origin to the circle, that because this is a unit circle, that hypotenuse would be 1. And that whatever this coordinate is, if this is the coordinate x, y, that to get, we would have to go x units to the right and y units up, right? So there's a relationship between the sides of this triangle and the coordinates that are right here. I'm going to draw this a little bit bigger. So let's draw this a little bit bigger. We don't know what this angle is. This is, if you've never seen that symbol, that's what's called a theta, which simply is an angle that we don't know. It's an angle we don't know. It's similar to like an x, right? We don't know what an x is frequently. Thetas are angles that we don't know in some sort of triangle. We do have a right triangle here because we're going along the x values and the y values. And we know that the hypotenuse of this thing is 1. So my question is, how would I find the x and the y based on what we know? This is where trigonometry comes into account. We should remember from geometry the relationships of our trig functions, which is frequently reminded and remembered as SOHCAHTOA. SOHCAHTOA. And what that means is that it's a way to help us remember the trig ratios for our three most basic trig functions. It stands for that sine of theta is equal to the opposite over the hypotenuse in a right triangle. Cosine of theta is equal to the adjacent over the hypotenuse in a right triangle. And tangent of theta is equal to the opposite over the adjacent in a right triangle. Again, these rules that we have here for SO, CA, TOA, sine, cosine, tangent only work for right triangles if you're using those ratios. Cool. So how's that going to apply for this particular problem? Well, in this case, what we can say here is if I wanted to find, if I'm using this angle that's right here, my sine, and I wanted to represent that for what we've got here, we could say that sine of our theta is going to be our opposite over our hypotenuse. Well, here's our theta. Our opposite is our y value, and our hypotenuse is 1. So that means that this is going to equal y over 1, or just our y value. So key sort of thing here is that y is your sine for a given angle. Similarly, cosine of theta is the adjacent over hypotenuse. If we think about our theta here, the adjacent is the x, the hypotenuse is our 1. So that's going to be x divided by 1, which is just x. And that means that it's the x value is going to be our cosine of theta. Well, what about tan? Well, tan of theta we know is opposite over adjacent. So if we're thinking about what we've got here, that's going to be our y value, it's the opposite of our theta, divided by our x value. So that's y over x. And that is going to be our third sort of relationship that we've got here. So tangent of theta is y over x for that. What does that mean? We have these trig functions. We've introduced it with this right triangle. What does that mean, and how does that help us with this whole unit circle thing that we've got? Well, we just said that for this sort of arbitrary triangle that we drew in the unit circle, that the x value of the coordinate for that triangle is the cosine for whatever angle we're talking about. And we said that the y value is the sine for whatever we're talking about. So that means that if you've got a point on the unit circle and you've got the coordinate, right, that x comma y, that really what that's telling you is the cosine of the angle comma the sine of the angle. It's telling you the cosine of that angle comma the sine of the angle. Which means, for example, if we take a look at our unit circle right here, we have this point right here. Right, that's a 30-degree angle or a pi over 6 angle, and I see that this is my x and my y. In general, on the unit circle, these coordinates are going to tell you whatever the cosine of that angle is and the sine of that angle is. So if I wanted to find cosine of pi over 6, we can take a look and we can see, okay, here's our pi over 6. Cosine is the x value. The exact answer for cosine of pi over 6 is root 3 over 2, because that's the x value at that point. Sine of pi over 6 is the y value. That's going to be 1/2. Right? We can see that right here. Nice, and that's true for all of the angles around the outside. So the unit circle is this really an amazing tool that allows us to find out what sine and cosine and tangent are using the values around the outside. And they give us these exact values that have these like root 3 over 2s or 1/2s or root 2 over 2s that even if we were plugging these into a calculator, the calculator would just give us decimal approximations. These are exact answers, and we were able to do that using these special right triangles from geometry class from a couple years ago. Okay, so we've got this. Let's jump into some examples, and I think that's going to wrap us up for today. So let's find the exact value of the trigonometric function. When they say exact here, we're saying don't plug this into your calculator. Your calculator is going to give you decimals. That's not exact. So sine of 7 pi over 4. Here's what I would do. I would go up to my unit circle. I would look for 7 pi over 4. Where is 7 pi over 4? It appears to be right here. We remember that sine is the y value here. So here is my 7 pi over 4. My y value appears to be negative root 2 over 2. So that is going to be my answer for this, would be negative square root of 2 over 2. We could find this on our calculator equivalently by plugging in sine of 7 pi over 4 and also typing in negative root 2 over 2, and you'd see that those are the same decimal. What about sine of pi over 3 for number 12? Sine of pi over 3. Well, I'm going to go to pi over 3. That's right here. And we see that is our sine is going to be the y value. So I'd be looking for that to be root 3 over 2 for that. Square root of 3 divided by 2. Well, what about cosine of negative 3 pi over 4? Remember, if we're talking about negative numbers, that means we're going in the negative direction. I'll erase what I've got right here. So what we can see is, first off, positive 3 pi over 4 is up here. So that would be going in the positive direction. I would end up at 3 pi over 4. If I went negative 3 pi over 4, that's going to be at 5 pi over 4. Negative 3 pi over 4 is the same thing as 5 pi over 4. And if you're not sure why that's the case, we can remember from earlier talking about coterminal angles. Right, negative 3 pi over 4. If we wanted to go in the positive direction around that circle, we could add 2 pi to it. But to combine these, we would need to, and again, sorry, 2 pi is a whole circle, right? That's where that 2 pi comes from. We would need these to be the same denominator if we're going to add them. So I could technically multiply by 4 and multiply by 4. And if I do that, I get that this is negative 3 pi over 4 plus 8 pi over 4. And now these have the same denominator, so negative 3 plus 8 is 5. So this is 5 pi over 4 for that. So what does that mean? Hey, those are coterminal angles. So I'm actually saying that cosine of negative 3 pi over 4 is the same thing as cosine of 5 pi over 4. And that's useful because 5 pi over 4 is actually on our unit circle. We can see that it's right here. And so at 5 pi over 4, our cosine is our x value, right? That's our x, that's our y. So that's going to be negative square root of 2 over 2 would be the answer for that problem. What about cosine of pi over 6? Pi over 6 we see is right here. Whew, went all the way up. Cosine of pi over 6 is right here. The cosine is the x value, so that appears to be root 3 over 2. Tan of 5 pi over 6. Well, we said that the tan was the y value divided by the x value. Let's see where 5 pi over 6 is. 5 pi over 6 is right here. And we see our x and our y. So it's our y divided by our x. How would we find tan here? Well, if we think about the y divided by the x for those angles, we see that that's going to be 1/2 divided by our x value, which was negative root 3 over 2. Our 2's cancel here. So this is going to be equal to 1 over negative square root of 3. But as we know from earlier in this, we can't leave a square root in the denominator. So I'm going to multiply by the square root of 3 over the square root of 3. And if we do that, that's going to be, looks like negative square root of 3 over the square root of 9, which is just 3. So negative root 3 over 3 would be our answer for that one. I'm going to end it there because I think this video has been already long enough. We are over an hour on this. This was a huge introduction to constructing and using the unit circle. Hopefully from this we've gone over, you should be able to convert from degrees to radians and back again. You should be able to identify what coterminal angles are. You should be able to find sine, cosine, and tangent using a unit circle, those exact values. And then hopefully you're able to construct the unit circle as well. But these things here in green are definitely skills that we should be able to practice and do after watching this video. As usual, please email me with any questions you've got. Have a great rest of your day.